So, hi all. What we're going to do now is we're going to see an application of the WKB approximation to quantum tunneling. And this will give you also an idea of how powerful this is. So this is going to be quite a technical derivation, but I hope you enjoy it. So let's start. So to start with, we are going to have a look at what we already know. So our previous studies of tunneling through a barrier were related to a square well. And what we had was pretty much that we had a potential of height V naught. So here we have Vx as a function of x. And this was a square well. And there was a particle of energy E, which was coming from the left, right? So we had region 1, region 2, and region 3. In region 1, we know that our wave function for this particle would be the incident wave function. So we have IPX divided by h bar. So we're considering a 1D problem here. And this is telling you that it's coming from the left to the right. And part of it was reflected. So the minus sign here tells you that this plane wave is going in the other direction. Once the particle is here, the situation kind of changes. And we're going to have some exponential increase and some exponential decrease. And finally, once it got through in region 3, there's nothing to reflect because you just had this barrier here. You have nothing here. And you expect it to go through. So we're going to have transmitted EIPX divided by h bar. So these are your wave functions. And just to remind you, P is the momentum of the particle, so it's 2mE square root, and Q is 2m V0 minus E square root, both real in this case as defined. Okay, so the constants that we have several constants. For instance, R, C, D, T, they are determined by boundary conditions. And these boundary conditions are the continuity of x, psi x, sorry, and psi x dash at the turning points. And this is something also we expect, because if you look, you see that here we just have one wave function in all space, and it should be continuous. But we know how we represent it in regions 1, 2, and 3. So what we need is continuity at the boundaries between these regions, which are these turning points here and here. And if you want to calculate tunneling rates, how do you do it? You consider that using the probability flux. So you have J 2IM psi star x d psi x dx minus psi x d psi star dx. So this is going to give you probability currents. Namely, the incident current which is Ji P divided by M, then reflected current GR R square P divided by M transmitted current GT modulus G square P over M and tunneling rate GI GT T square. Now what we would like to do is to generalize this to an arbitrary potential that is smooth enough according to the definitions that we have already seen. So we're going to look at generalization using the WKB approximation. So let's have a look at our potential. We have once more Vx and V and X, sorry, but it looks quite different now. You don't have square root anymore. You have something that is like this, that is smooth. And we consider once more that we have a particle of energy E. And this is going to give us these two turning points. A and B. And we're going to have 3 regions. So we're going to have region 1, which is classically allowed, region 2, which is classically forbidden, and region 3, which is classically allowed again. And we are going to assume that the particle is coming from the left in the classically allowed region. So we're going to have the following situation. Particle is coming from the left. At some point, you have to make some assumptions, and it is traveling from the classically allowed region 1. So if we are considering this, let's see where is our easiest place to apply our connection formula. We have seen we have connection formula. We have seen that they need to satisfy some conditions asymptotically. Now we have region 1, region 2, region 3. We have a particle that is traveling from here, so something is going to get reflected, something is going to get transmitted. But here we know that we only have transmission, we don't have reflection, because there's nothing here on the right that is going to reflect this. So one thing we know for sure, we know what to expect in region 3. And we can say that psi 3 x can be given by the WKB wave function, where A dash is an arbitrary constant, and we have then exponential from x to the turning point. Note that x is bigger than the turning point, so this is going to be exponentially, no, this is not, this is going to be traveling, px dash dx dash. We have something that is going to be traveling from, this is the other way around, hang on. Should be like this. B and x. Okay. Now, we are fine with that. And we know that this is arbitrary. And we have seen all these phases that you get in your expressions from the connection formula. So we have some flexibility. And we're going to make a choice of arbitrary constant, which is going to make it easier for us to apply the connection formula. So it's easier to apply the connection formula if A is equal to A dash EI pi divided by 4. So this is going to give you then psi 3 x. We're just rewriting it, okay? So that is going to be nicer for us later on. Px exponential I divided by h bar from b to x, p x dash gx dash. Once more, this is a dummy index. This has nothing to do with derivatives. It's just a way of expressing this variable, and I pi divided by 4. Okay, So we're going to use as well, using the Euler formula, which is EI theta is equal to cos theta plus I sine theta. We find that psi 3x is a square root of px cos bx p x dash gx dash divided by h bar minus pi over 4 plus I sine theta, where theta is bx px dash gx dash divided by h bar minus pi over 4. Fair enough. Now we want to go to region 2. And the thing that you should do is have always those tables and identify if you want to apply connection formula, if it goes with the arrow or if it goes against the arrow. So we have seen that if you have a cos on the classically allowed region and then you go inside left hand barrier, which is what you're going to have. So region 2, you have a barrier if you go from region 3 to 2 that looks like this, right? So it's what we call a left-handed barrier, which means that here you have something that is classically forbidden, and here you have something that is classically allowed. Okay, so let's do this and let's write the wave function in region 2. So if we write that down, we find something like this: a square root of qx. I'm just using the connection formula, so I always recommend that you have a look if it's not in front of you. 1/2 exponential minus integral from x to p q x dash gx dash h bar minus I exponential x b q x dash gx dash over h bar. Okay, so now we're going to analyze and see which goes with the arrow and which one goes against the arrow. Okay, so this one, if you look at the expressions that you have, this goes against the arrow. So let me write against the arrow. And this one followed the arrow. I told you in the previous lecture that you have to be careful with this, with the arrow, but sometimes you can go against the arrow because you know how psi 3 has to be. So it's again a question of common sense, and is a question of knowing what you're doing. And I'm going to put some observation here. You have to be really careful with these things because the arguments for having those arrows is that sometimes if you go from the classically forbidden to the classically allowed region, you may get the wrong solution. But in this particular case, we went against the arrow because we know that psi 3x, this means x, psi x in the region 3, has to be a traveling wave. So that's why we started actually from region 3, because we didn't want to have any kind of ambiguity. One could ask ourselves, why don't you start from region 1? Well, we still have something reflected, right? But region 3, we know that we have to have a traveling wave and that we are not going to have any reflection. So it's something we already know. And normally, the arrows exist or are present to avoid spurious amplifications on the other side of a turning point. So you have to be careful. And the best way to start solving a problem where WKB is used is to start from a region where you really have no ambiguity with regard to the solution. Because then you can do certain things, but you must be careful. And now we know how it looks for region 2, kind of. How about region 1? Let's try to write this for region 1 then. So in region 1, we're going to write the wave function, but we need to do some tweaking in the wave function region 2 so that we are able to use the connection formula. Okay? So first things first, to apply, well, we need to write psi 2x in a way so that the limits of the integral allow for the connection formula to be applied. Okay, so what we have is we have integrals going from x to b, meaning x from this turning point up to the turning point, and we need to write it in a function, where the integral goes from a to x. So let's do that, and we're going to use the following. We can say that exponential integral from x to b qx dash dx dash divided by h bar can be written as exponential from a to b qx dash dx dash h bar times exponential from minus a to x qx dash h bar dx dash. right? Now we can also say that this is, we can also call this guy R, so that this is equal to R exponential minus ax cubed x dash dx dash divided by h bar. Okay, so if you have all these, we can also write, we can multiply and divide by R, and we can write psi2 a bit differently. So write psi2x as a square root of qx 1 over 2r exponential So we can write this. Remember that this is a negative exponential, so that's why this has landed here. 1 over 2r exponential a up from a to x cube x dash gx dash divided by h bar plus minus ir exponential integral from a to x q x dash dx dash divided by h bar. So we are now in a position to apply the connection formula across a right-hand barrier, because now we want to go from 2 to 1. And from 2 to 1, what we have is we have this turning point here. So we have 2, we have 1, and this is a right-hand barrier, because here you have something that is classically forbidden, region 2 actually, and region 1 is classically allowed. So let's have a look at this connection formula, and we find then that psi1 x is a. So what we want to see is how we connect this guy with whatever we have on the left-hand side. And it is going to give you p square root of px minus 1 over 2r sine xa p x dash gx dash over h bar minus pi over 4 plus minus 2ir cos from integral x to a p x dash gx dash divided by h bar minus pi over 4. Okay, but we would like to write psi1 in terms of traveling waves, because this is something that is going to be more useful for us if you want to make a connection with the square wave, and also physically speaking, because we need to compute this tunneling. And we do have traveling waves. So let's have a look at how this can be written. So let me write this in terms of traveling waves. And what we can do is let's consider psi x from h to, sorry, the other way around, from x to a p dash g x dash divided by h bar minus pi over 4. So that is just to make it easier for us then to manipulate this, because we're going to use the Euler formula again in terms of bringing sine and cos now to write it in terms of complex exponentials. So do check this. I'm just going to put the result, and we're going to have px minus 1 to r sine phi x minus 2ir cos phi x. Remember that this is e I phi x minus e minus I phi x divided by 2y, and this is e I phi x plus e minus I phi x divided by 2. Okay, so bringing these out together and grouping this in terms of exponentials, we have then that this is going to be IA over, let me write this nicely, IA over square root of px (1 over 4r minus r ei phi of x minus 1 over 4r plus r e minus I phi x. Why am I doing this? Because what I want to show is that when you take the limit of this, that you are going to have reflected. I want to find what is reflected. I want to find what is coming from the left, and I want to calculate all those currents that I wrote at the very beginning. That's my main objective, in fact, of doing this. I'll pose these questions here. Which is the incident and which is the reflected wave? What we need to do is we need to calculate the limit taking x to minus infinity of both. But I'll do for e phi x. You should have just one minus infinity. And we are going to assume that v x tends to a constant V naught. So far, so good. Because in this region, then we can say that Px is also approximately constant. So if V approximately V naught, let me make this Vx to make it clearer. Then we know that Px is going to be approximately P naught, which is going to be then defined by 2m square root of 2me minus V naught. So far, so good. So what I'm going to do is I'm going again to split this integral, and I'm going to write, note that you have an I. So you can write your EI phi x as E minus I pi over 4 exponential I from x to a p x dash gx dash over h bar. And I can split these things too. So I can say, I'm taking here this integral from x to the turning point A, and I can write this to be equal to integral from x to x naught p x dash g x dash divided by h bar plus x naught to a p x dash g x dash divided by h bar. So what I'm gonna do is I'm going to write this as approximately. We said if you are going from x naught to x, whereby x naught is bigger than x, which is this region here, right? We're bringing from x going to minus infinity to x naught, where x naught is the coordinate for which the potential starts to behave approximately constantly. So I can, because let's just remind us that V approximately constant, I wrote something wrong, approximately constant in this region. Hence, this integral is approximately P naught x 0 minus x divided by h bar, because then P naught is approximately constant. If you look at this thing that we have done here on top. And this means that if we bring all this together, we can say that E I phi x is approximately E minus I pi over 4 x I going from x naught to the turning point, p x dash dx dash over h bar, multiplied by this other guy, which is e to the power I p naught x naught h bar e minus I p 0x divided by h bar. Now, what you can see is the following, that this integral, whatever it is a constant, because you have these limits here quite well defined. One is a constant x naught, and here you have a, which is the turning point. This phase is also a constant, but this is varying with x, so that when you go for x between minus infinity and x naught, which is also negative and large in terms of absolute value, you're going to get that this thing is going to be proportional to minus ei p naught x divided by h bar. So that I know, actually, and this is not that intuitive, I know that this is my reflected wave, not the incident wave. So that's why you have to calculate these limits, because you have to be a bit careful. Correct? And this is weird, because now we can write the following. We can write, and we know which one is reflected, and we know which one is incident. So we can say that the function for wave function for region 1, so let me write this, wave function for region 1 is psi x1, which is equal to psi ir or x plus psi r x. And we know which one is reflected. So this is incident, and this is reflected. So we went through this trouble to identify which one is reflected, because we want the other one. So if you consider that this, let me look at the expression, and we know this is the reflected wave, which we have just shown by this limit. This is going to be the incident wave. So we can have a look. So if you consider the incident wave, in the region, so incident wave for x much smaller than x naught, so it's far away from the barrier, but x is negative, don't forget that. We're going to have that psi incident is going to be minus IA. That's where we had the minus I pi over 4 P naught EI alpha 1 over 4R plus R EI P naught X divided by H bar. Now, we just managed to group all these phases together. So we can say that EI alpha is equal to EI pi over 4 exponential minus I XA X0 to A P X dash D X dash H bar exponential minus I P0 X0 divided by H bar. And this is a constant phase, and that's what we had also in the other case. So we took the trouble to calculate all these limits because we could see we had constant phases. We could, in principle, make the same assumption on the right side, on the right-hand side of the barrier, right? So we have some expressions when we take x to minus infinity. How about taking x to plus infinity? So let me write here, region 3, right hand side of the barrier. Okay, so let's see what we get. Let's assume also that Vx tends to V0 if you take x to plus infinity. And we can say that psi 3 is of x is approximately a p0 e I alpha dash e p0x over, so it's actually propagating, and this e alpha dash, these are phases which are not relevant for what we're going to do, because now, why are we doing this? Because we want to calculate probability currents for incident and transmitted regions. So that's why we went through all this trouble to find what is incident, what is transmitted, right? If you look here, you see what is incident. This guy is incident, right? And this, if you wish, is the coefficient of this being incident. Now, transmitted, this is transmitted, correct? So if we write, so we know what are the transmitted and the incident wave functions. Okay, so we know that. Let's do some computation. Let's say we consider now Ji incident. We have that coefficient, so what we have to do is we have to take that coefficient and get modulo square and multiply it by p, which is going to be p naught. So if you remember, you had the incident coefficient square divided by m, and here you had p, which is going to be p naught in our case. So if you get all those coefficients, then you're going to find that this is going to give you a square divided by m, 1 for r plus r square, and J transmitted, you pretty much do the same. So J transmitted is going to be transmission coefficient square P naught divided by M. So this is going to give you A square divided by M. Therefore, if you want to calculate this, we're going to have, what is your transmission coefficient? This is going to be we are interested, so quantity of interest is then GT divided by GI. And this is going to give you 1 over 1 for R plus R squared. Now, we need to make some more approximations, because also you cannot be too close to the barrier. So we computed something which is on the left-hand side of the barrier and on the right-hand side of the barrier, and we took the asymptotic behavior to find what was transmitted and what was incident and what was reflected. So if we are looking at WKB, our turning points have to be must be well separated and the barrier must be then significantly higher than the energy of the particle. Which means that in such a domain, I mean, just think about it. We have here a barrier, we have A, we have B. If we are close to the top of the barrier, these turning points, they get closer and closer and closer. So we really need to guarantee that they are well separated, which means that if you calculate the integral R, which is an integral of qx dash dx dash going from one turning point to the other, it has to be big. Just to remember, so thus R, which is exponential integral from a to b qx dash dx dash divided by h bar, this has to be bigger than 1. Okay, so if this is bigger than 1, we're going to find that JT, JI is going to be approximately, make it approximately 1 divided by R squared. And this is going to give me E minus 2 integral from A to B q x dash gx dash divided by h bar, which is E minus 2 lambda, and lambda is a b q x dash g x dash divided by h bar. This is a very important formula, because what you can see is that there is a probability that this tunneling happens, and this is proportional to the width of the barrier. Okay, so we can make a statement that the transmission coefficient is, or the tunneling coefficient if you want, is related to the integral of Qx across barrier. This is quite important. This is something you see in many instances, and also when you're doing things that are quite advanced. So this expression which we have obtained is telling us that, so if you want, you can call it tunneling coefficient too. And you are going to see this in many instances in your life. So we're still going to have a few things related to WKB approximation, especially in the synchronous lectures and exercise sheets. But our next topic is going to be non-classical light. And I hope you enjoy it. It is quite fun, and we're going to use also a lot of the formalism that we have seen. Thank you.